All right, today's going to be a fairly short lecture, I think. I want to just cover like resonant harmonic motion real quickly, and then from there I'll just give you some more practice problems to do. Remember we talked about spring harmonic motion and then pendulums as harmonic motion. And so a leg is a pendulum. Now, notice here's something interesting. Imagine you have like just a bob hanging from a string, and you start wiggling your hand back and forth. The pendulum's going to start swinging. And if you do it just right, you can make it swing faster and faster. If you do it wrong, you just stop the motion totally. Now, blah, blah, it starts out with very small oscillations. But then as you move your hand back and forth, the oscillations get bigger and bigger and bigger. The reason why is because you're applying a force on it that is in resonance with its motion. I don't like the way they're saying this, so I'm going to draw a picture here. Oh, get rid of my chemistry first. A similar situation is you're pushing someone on a swing. Okay, so there they are hanging from the swing. They pull back to here and release, and they'll swing there and back and forth and back and forth, and they'll become a pendulum, right? Now, again, assuming no friction up here at the pivot point, the person on the swing is going to swing back and forth forever and ever and ever. Same amplitude, the whole works. But what if you stand back here as a proud parent and push? Every time the swing pendulum comes up here and starts going back down, you give it a little push. Now, the restoring force is already pulling in this way, which would normally bring it just back right up to over here. But you gave it a little extra force, a little extra nudge. So that increased it, made it go faster through here, and so it comes up over here a little bit higher than it did before. And then goes back, and you give it a little push again. And it's going to go up a little higher again and again and again. And what you've done is you've increased the amplitude of the harmonic motion. Now, notice the period stays the same. We already discussed that last week. The period doesn't change with amplitude. So whatever the period of this pendulum is, maybe it's exactly 1 second based on its length, it's going to always be 1 second. All you're doing is changing the amplitude of oscillation. Notice another way to say that is you're applying a force exactly in step with the period. If the period is 1 second, you're applying the same exact force every 1 second. If you were to apply that force, now obviously you'd have to run around to do this, but if you were to apply that force at different times, every 0.8 seconds or something like that, you would hit the swing at different times in its swing. And so you might hit the swing right here when it's moving the wrong way. And at that point, your force actually slows down the pendulum rather than speeding it up. Or we say you're applying a damping force when that damps the motion. But if your force is always in resonance with the swing, always at the same point in the period, it will build up bigger and bigger and bigger. And we have resonant harmonic motion. Okay? If you apply it against the motion, you have damped harmonic motion, where you actually damp the motion and slow it down. Now, simple harmonic motion, life is real easy. It's just your basic wave function that we're going to look at starting probably tomorrow. When you start dealing with resonance or damping, things get exponential real quick. Okay? You'll find for resonant harmonic motion, you'll find there's an e to the kt term, where t is time. So as time goes on, that exponent on e gets larger and larger and larger, exponentially, duh, because of the name. And so your oscillations will grow slowly to start with, but once they start getting rapid, they start getting rapid out of control. Okay? So because this is an exponential growth, when you first start doing it, it swings up a little bit, then a little bit more, then a little bit more. But if you remember what exponential graphs look like, they do that. And so once you turn that corner, then the oscillations grow in amplitude extremely rapidly with each push. Obviously, you wouldn't do that with someone on a swing because, well, just physically it wouldn't work real well. But if the oscillation is like a sound oscillation or a vibration of a bridge, and if there's a resonance force involved there, it could literally shake the bridge apart, as the Tacoma Narrows Bridge did, if you know that situation. One of the goals of engineering, for you engineers out there, is damping harmonic motion. Let's say you have some device with a motor mounted onto a desktop, and as that motor is running, it vibrates and shakes the desk and makes noise, and the whole works. If you can provide a mechanism that will damp that harmonic motion, that will provide a force as opposed to the vibration, that will quiet the motor and make the desk not vibrate around also. If somehow you manage to, instead of damping it, you manage to resonate with it, you could literally shake the whole thing apart. Okay, and sometimes that happens. You don't want that. So that's resonance and damping. Now, I think I covered it a lot better than they did anyway, but real quickly, you can look at the PowerPoint on your own. The Tacoma Narrows Bridge, in the 1940, I guess it was. I mean, it was a while ago. There it is. It was a bridge across a valley or a gorge of some sort. And now, every bridge is going to swing with the wind like a little bit of a pendulum. In this case, the oscillations of maybe the wind blowing underneath it or whatever were perfectly in resonance with the vibration frequency of the bridge. And so the bridge vibrated, and then the vibrations got bigger, slowly and slowly, bigger and bigger and bigger, until eventually, you can look up videos of this, they're on YouTube. You can see the bridge actually vibrating, going up and down like a wave. You can literally see the waves rippling along the bridge. And obviously that's not good for the structural integrity of the bridge. And eventually the whole thing just tore itself apart as you see pieces of the bridge laying on the ground below. So again, like I said, I don't have a whole lot to talk about today. I just wanted to mention the fact that we're dealing with simple harmonic motion. When you deal with resonant harmonic motion, you get that e to the kt term where the exponential growth eventually makes it grow out of control. And when you do damping of harmonic motion, you get e to the negative kt. So as time gets bigger, the exponent becomes a bigger negative value, so a smaller value. And now you get an exponential decay curve, which looks like an exponential decay curve looks like this. Okay, so it drops off real rapidly and then just steadies itself out somewhere, approaching the an asymptote down there, not necessarily the axis. So anyway, that's that. I'll leave it at that for today. And for your practice problems, I'll just give you some more pendulum and spring problems to play around with to make sure you're okay with all that. Okay, and that will do it for today.